What up, peeps? One more time. Today we're going to be talking about the different kinds of the sets of numbers. And I'm just going to start out very basic and work up to the more involved types of numbers. Well, first of all, we're going to talk about what are called the natural numbers. Natural numbers are just the numbers that you learned about when you were a very young child. They start with 1, and they just proceed 2, 3, 4, and so on. Essentially, we're talking about the counting numbers, right? So when you first learned about counting apples or brownies or whatever it was when you were a kid, natural numbers. And if I'm going to abbreviate the set of natural numbers, some of the sets of numbers can be abbreviated using a symbol. In the case of the natural numbers, this is a very large capital N with an extra bar there on the side. There's the natural numbers. And then from there, we're going to go to the whole numbers. And the whole numbers are essentially the natural numbers, but also with the number 0. We start with 0, we go to 2, 3, and so on. Right? So they're the same set of numbers, but with one minor exception that 0 is considered a whole number. There's not an abbreviation for whole numbers. Oftentimes, we'll say that the whole numbers are just the natural numbers plus the number 0. Right. Now, what about the third set of numbers? Integers. Integers are essentially the whole numbers, but the positive whole numbers, 0, and also the negative whole numbers. So any of the numbers that are like typically where you'd mark on the number line are going to be your integers. So they start, there's an infinite number of negative, and then we go to -2, -1, 0, 1, 2, and then of course all the way up to infinity. And then of course the integers, that's abbreviated with it's represented with a set of all integers, just this v with an extra little bar in it there. And interestingly, that's and you think, well, why would the integers not be an I? Why would we use z? And it actually comes from the German word for integer, which starts with a z. And if you're interested in more about that, then you can spend your own time looking that up, or maybe I'll do a different video on that. But anyway, integers, big Z. Let's see. After integers, we have the real numbers, and the real numbers. I'm gonna have to describe the real numbers. The real numbers are essentially any number that can be represented on a number line. Any number that can be represented on a number line. Oh, you know what? I skipped one. I skipped the rational numbers. Well, I'll talk about real numbers real quick, and then I'll go back and talk about rational numbers and numbers that are not irrational. But essentially, real numbers, any number you can put on a number line. That includes any of the integers, any of the numbers in between, whether you're using decimals, if it's fractions. Pi is an example of a number that's a real number, even though you can't really write it as a decimal without having to stop at some point. That's the way that goes. So in the real numbers, you use a giant R with an extra bar in it for the real numbers. The real numbers are actually broken up into two kind of subsets of real numbers. One of them are the rational numbers, and the others are irrational. And rational numbers. I'm going to go scroll this down. I'm out of space. Oh no! All right, I gotta get more space here. So let me go ahead and make a new thing. So we're on rational and irrational. I'll make a new document here. I'm not saving this. No. Okay. Good. And yellow. All right. So rational numbers. Rational numbers are any number that can be represented as a ratio of integers. So essentially fractions, where the numerator and the denominator of the fraction are both an integer. And interestingly, like most numbers that you can think of, probably off the top of your head, are going to be rational numbers. Not all of them, but many of them. So like, 2/3 would be a rational number. If I put like 0.01, you think, well, that's a decimal. Is that a rational number? Well, you can write it as 1/100. So of course, 1 and 100 are both integers, and so that's a rational number as well. And really, any decimal that terminates or repeats is a rational number because it can be expressed as a ratio of integers. And the rational numbers, we use a giant Q with an extra bar to represent the rational numbers. Because R is already taken, right? Because of the real numbers, and then of course we're taking the quotient here, so Q kind of makes sense for when we're dividing. So what about numbers that are irrational? And so irrational, we don't have a special number for those, so a special letter. But irrational numbers, take a look here. Essentially, numbers that cannot be expressed as a rational, right? So not a ratio of integers. And so some examples of these are pi. Pi would be an irrational number because even though I have common, students are often accustomed to expressing pi as roughly 3.14. Notice we have to say that it's approximately equal to, because pi actually, if expressed as a decimal, is non-terminating and non-repeating. So anytime we have to express a rational number as an irrational number as a decimal, this is how we do it. We have to approximate. Similar with like E. E is approximately 2.18281828. But again, it's not equal to that. And then essentially, this is another set of irrational numbers you're going to come up with anytime. Anytime you take the square root of an integer that isn't a perfect square, that will be an irrational number. So the square root of 2, the square root of 7, the square root of 11, even the square root of, even if I said like the square root of, 32, right? Even though there's a component of that is a perfect square, there's a factor, right? We write that as radical 16 times radical 2. That radical 2 part, that factor, cannot be expressed as a ratio. So radical 2 is another example of an irrational number. And so that's all the types of numbers that you learn about typically up until you get into algebra 2. And then there's one more set of numbers that we have to consider. And for those, we have to ask about how how we take the square root of numbers, right? So if I take the square root of a negative number, typically whenever we're asked something like, let me get my pen here. In class, you're asked to find the solutions of x squared plus 1 equals 0. Well, you can't actually find real solutions to this, because if you subtract 1 from both sides and you take the square root of both sides, the square root of x squared equals the square root of negative 1. And of course, the square root of negative 1 doesn't exist. That's non-real. And oftentimes we just say, well, that's no solution to this problem, right? You can't take the square root of a negative number and you're good to go. However, if we define the square root of negative 1 as I, right, we say, well, let's suppose we can take it, and we'll just call this I the imaginary unit. Now we can take the square root of negative numbers, and so this gives rise to a newer set of numbers beyond the real numbers, and that are called the complex numbers. Right? And complex numbers are essentially numbers that are that involve this imaginary unit. So, for example, an example of a complex number would be any number. So I'll just put it this way, right? It can be expressed in the form a plus bi, of course, where I is the imaginary unit, where a and b are real numbers, right? So this allows you to take this allows you to express the solutions to quadratics that don't have real solution. Again, the new set of numbers, the complex numbers, and the complex numbers are expressed. The abbreviation is a big C with a line. Oh, I'm at my limit. Well, luckily I got it in just under the wire there. Come on, hide this. Let's go. All right, it's been a good time. Hopefully you learned something, and if not, well then that just shows these videos. Maybe I should do a better job, or maybe the videos aren't so good to begin with. Anyway, thanks. Good luck, peeps.